Good morning, my dear students. Today, I'll solve few examples related to ideals. Before I solve the example, uh, we must able to understand the definition of rings, then subring. Okay, to define a subring, what we need? We need a ring satisfying two conditions. Under addition, closure law must holds good. Under multiplication, the closure law must holds good. Let me start. Thanks. Let me work out the example. Let R be a ring. R be a ring means all the laws of the rings are satisfied. Let here we have a matrix of 2 by 2. That means 2 rows and 2 columns. But here the condition is the second column elements are strictly 0. The first column elements A and B both are integers. We have to show that it is left ideal but not a right ideal, but not a right ideal of a ring R. To work out this example, we needed to take two matrices of the same type. Let A is a matrix. A is a matrix containing the elements A1, B1 in the first column. Second column strictly 0. The matrix in the matrix B, the first column elements are A2, B2. Second column elements are strictly zeros. Okay. Here all the elements, that means A1, A2, B1, B2 are integers. Let me verify the subring condition. I will take the difference of these two matrices. A minus B. You know how to work out the examples. That means A minus B. First row, first column element with first row, first column element of second matrix. That is A1 minus A2, the first column. B1 minus B2 in the first, second row, first column element. And second column elements are strictly 0. Okay. Now, if A1 is integer and A2 is integer, definitely the difference of these two elements are integers. B1 is integer, B2 is integer, the difference of these two elements is also integer. That means it belongs to the set N. The first condition holds good. Second condition, the product of these two matrices. The first, if you multiply these two matrices, what we get in the first row, first column? A1, A2. In this second row, first column element B1, B2. Again, it belongs to what? N. Belongs to N means it is same as the set N. Hence, the N, I mean the given set N is said to be a subring of what? R. Now we have to verify the second condition of an ideal. Let me take a matrix of the type X, Y in the first row, Z, T in the second row. Okay, I'll denote it, this matrix, by a letter R. I mean the element R is an element of R. Let me work out both. RA. You see what I said in the definition? The element of R appears on the left hand side treated as a left ideal. If it is on the right hand side, treated as right ideal. RA. The product of R and A is what? XA1 plus YB1 ZA1 plus TB1 in the first column. Second column elements 0. Okay. Clearly X1 XA1 plus YB1 ZA1 plus TB1 is an integer. I mean both are integers. That means it is a left ideal. Clearly it is a left ideal because again it is a member of what? N. Now let us consider AR. AR, I'll take it as 1, 2 in the first column, 0, 0 in the second column. Strictly the second column element must be 0 because it belongs to n. Or here I'll take 3, 4, 5, 6. If you multiply these two, what we get? 3, 4 in the first row, 6, 8 in the second row. To say belongs to n, let me recall, to say belongs to n, the elements should be of the form, what? A, B in the first column, strictly the second column elements are what? Zeros. Okay, but here we'll not see like that. In the second column, we see 4, 8. That means it does not belongs to n. What it shows? This example shows that it is not a right ideal. Try to work out this second example. Here in the second example, what I have taken? The first row elements are AB. The second row elements are strictly 0. If the example of this nature, it is right ideal but not what? Left ideal. Try to work out this example. Okay. Now I will take important results related to the ideals. Intersection of two left ideals. The first result. Let I1 and I2 be two left ideals of ring R. I1 is a left ideal of ring R. I2 is also left ideal of ring R. We know that every left ideal of ring R is a subring. Very clear, it may be left ideal or right ideal, basically it must be a subring. Since it is a left ideal, therefore it is a subring. Clearly, what it shows, the intersection of these two ideal is also a subring. Now, if A is a member of I1 intersection I2, that means what? I1, A belongs to I1, A belongs to I2. Since it is a left ideal, since I1 is a left ideal of ring R, that means we need to check the condition of left ideal. R belongs to R. Remember, R belongs to R. A belongs to I1. Definitely their product RA. Here we see R on the left side of left hand side. RA belongs to I1. Since I2 is a left ideal, I will make use of the definition of left ideal. R belongs to R. A belongs to I2. Definitely their product RA belongs to I2. RA belongs to I1. RA belongs to I2. That shows that RA belongs to I1 intersection I2. What it shows, if I1 and I2 are left ideals, definitely their intersection is also left ideal. Now I'll take right ideals. Let I1 and I2 be two right ideals of ring R. We know that every right ideal is a subring of R. Therefore, their intersection is also subring. Let me work out mathematically. A belongs to I1 intersection I2. That means A belongs to I1 and A belongs to I2. To verify the second condition of ideal, right ideal, take an element of R. That means R belongs to ring R, A belongs to I1, their product also belongs to I1. Similarly, AR belongs to I2. What it indicates? AR belongs to I1 intersection I2. To check whether it is left ideal or not, we have to take an example. You take Same example which I solved in the earlier, but only thing is we have to I'll take AA as 1 2 in the first row, 0 0 in the second row, 3 4 5 6 as it is. Check it, you'll get the answer. That means this example is right ideal but not left ideal. Now I'll take another important result. Field has no proper ideals. Field, you know the definition of field. Field means a commutative ring with unity, and every non-zero element has a multiplicative inverse. Field has no proper ideals. That means field has only improper ideals. In other way, we can define this statement like this. If F is a field, then its only ideals are the set containing additive identity and F itself. All will give same meaning. F has no proper ideals is same as saying F, the field has only improper ideals. In other words, if F is a field, then its only ideals are the set containing additive identity and F itself. To prove this theorem, what I do now, I take an ideal. Let I be a non-zero ideal of the field F. Let me consider a non-zero ideal of the field F. I need to verify any definition, or to check the definitions, we need to take elements. Non-zero ideal, that means non-zero element. Let A is not equal to 0 be an element of ideal. That is, generally we denote the ideal by notation capital I, just to understand or just to remember. Since it is an ideal, therefore it is a subring. If it is a subring, 100% it is a ring. That means it has an inverse element. Here, A inverse belongs to F, A belongs to I, A inverse belongs to F. Therefore, their product A dot A inverse belongs to I. A dot A inverse means unity, that is 1 belongs to I. Let me recall here. Clearly, A inverse belongs to F because it is an ideal. Remember, since I is an ideal, therefore A inverse belongs to F and their product belongs to I only. Let X belongs to F. X is a member of F. 1 belongs to I. 1 dot X belongs to I. That means what? X belongs to I only. What we observe here, if X belongs to F, then X belongs to I. What it shows? It shows that F is contained in I, not subset. Remember, whenever I write like this, it shows that F is contained in I, but by definition, I is always contained in F. What it shows? F is contained in I, but by definition I is contained in F. This shows that I equal to F. What it indicates? It indicates that it has only improper ideals. That means no proper ideals, or in other words, the only ideals of F are the set containing additive identity M and F itself. One example, show that the set of integers, and we denote it by Z, is not an ideal over ring Q. Here the ring is set of rational numbers. Whenever we see the word ring, we see two binary operations, addition and multiplication. Let me check the definition. I need two elements. A is the first element B is the second element. I'll take A as 2 and B as 3. The difference of these two is minus 1. Minus 1 is an integer. If I take the product of these two is 6. 6 is also an integer. Hence, the set of integer is always a subring. Set of integer is very friendly because it is a ring, it is a subring, and it is a what? It is an ideal and so on. To verify the second condition of ideal, I need an element from Q. Let me take a rational number 4 by 5. You take any rational number as you wish. Let me take a rational number 4 by 5 and I'll denote it by R. AR. What is AR? Product A is 2. R is 4 by 5. Therefore, their product is 8 by 5. 8 by 5 is not at all an integer. That means it does not belong to Z. Similarly, if I take RA, again we get the same 8 by 5. It is not an integer. Therefore, this example shows that this is neither left ideal nor right ideal. That means this is not an ideal. Now, another definition: principal ideal ring. To define a word that is principal ideal ring, we need a ring. Fine, because the word ring is that. Next word, ideal. We need to know the definition of ideal. Now, finally, the principal ideal ring. What is, now the question arises in our mind. What is the meaning of principal ideal ring? To define the word principal ideal ring, a commutative ring with unity and without zero divisors. A commutative ring with unity and without zero divisors, that means clearly an integral domain, is said to be a principal ideal ring if every ideal in a ring R is a principal ideal. Now the question arises, what is the meaning of principal? What is the meaning of principal ideal? Principal ideal means an ideal is said to be a principal ideal if it has a generator. Generator means any ideal generated by single element. For example, whenever I use the word generator, I will put this A inside the bracket. That means the set containing the multiples of A, that is AR, or we may take it as RA. For example, I'll take as 5, generated by 5. I is generated by 5. That means multiples of 5. Multiples of 5 here give, that is 5n. Give different values to n. What do you get? 5, 10, 15. Okay. The right hand side. Left hand side 0, minus 5, minus 10, minus 15 and so on. So this set indicates generated by an element 5 or generated by an integer 5. Prime ideal. Prime ideal, again to define a prime ideal, we need an ideal. Let R be a commutative ring. Let R be a commutative ring. An ideal P, since we have the word prime ideal, I will take the notation P. An ideal P of ring R is said to be a prime ideal of R if it satisfies this condition. The condition is this: if AB means product of these two elements belongs to P, that means either A belongs to P or B belongs to P. Let me take an example. Generated by 15. Generated by 15 means multiples of 15. Multiples of 15 means what? 15n, where n belongs to Z. what we get? The set containing the elements of the type 0, 15, 30, right hand side, left hand side, minus 15, minus 30, minus 45, and so on. Clearly, this example shows that it is not at all a prime ideal, because 15, listen to my words carefully, 15 is a member of this set, yes. 15 can be written as 3 into 5, but 3 is not a member of yes, and 5 is not a member of yes. What we observe here in this example, yes contains the multiples of 15. That means it is generated by 15. Okay, the elements of S are 0, 15, 30, 45, minus 15, minus 30, minus 40, and so on. Okay, let me take one element. Let me 15. 15 is a member of S, and 15 can be written as 3 into 5. Neither 5 belongs to S or nor 3 belongs to S. That means both are not the members of S, but their product belongs to S. This example shows that what it shows? This example shows that it is not a prime ideal. Okay, but to say prime ideal, what is important? Out of two elements, one must be the member of that set. Thank you.